Evening. Welcome back to Elementary Algebra. I'm your instructor, Amy Fuchsteiner. We are currently working on solving systems of equations. That is 2 equations, 2 variables. And we're about to start section 4.2, which is solving a system of equations using a technique known as substitution. Alrighty, so in section 4.1, we graphed lines. We graphed a lot of lines, and we found solutions to systems of equations by graphing those lines. The point of intersection between 2 lines represents the solution to that pair of equations. Now, we did run up against a couple of situations where there either wasn't a solution or where the lines literally landed on top of each other from beginning to end, and there were infinitely many different solutions to that system. Now, today what we want to do is we want to look at those same outcomes using a slightly different method. We're going to look at substitution method. Now, why a different method? Well, graphing is great for showing you the different the different solutions to the systems. When it comes down to the nitty-gritty of the mathematics, though, we don't always have an option of graphing. Like, we don't always have graph paper with us. And as I think you saw in some of the last examples there, oftentimes when you graph a system, if the solution doesn't line up perfectly on the corners of your grid, you can't really tell where it is. And if you're trying to check it and make sure it works, it's really hard to make sure it works when you're close, but not exact. Like, you think the answer might be 1/3 and 7/8, but it's really 1/2 and 3/4. Like, you just spend so much time getting frustrated. So we need alternate methods. And one of the very popular alternate methods is the substitution method. So what is the substitution method? Well, again, you have 2 equations and 2 variables. So the idea with the substitution method is to solve one of the equations. Oh, hold on. Okay, that's the best it's going to do. Sorry, don't mean to give anybody vertigo. We're going to solve one equation for one variable. How do we know which equation and which variable? We'll talk about that. It's usually pretty easy to see. Like, you look at it and you go, oh, okay. So there's a little bit of a trick to knowing, but once you see it, you see it. So we're going to solve one equation for one variable, and then we're going to substitute that value, or in some cases, that mess, into the other equation. This should leave you just a singular variable. That's going to leave you a singular variable to solve for, and once you've solved for that, we're going to put that solution in to find the other variable. Basically, it's an escape room. We're going to solve one part of the puzzle, and then we need that solution to solve the next part of the puzzle. Have you ever done an escape room? Yeah. Okay. If it ended where they just gave you the solutions, that's not the way this is going to end. You're going to have to find the first solution yourself. I just want to be clear about that. Okay. I'm going to go through a couple of examples, and we'll see how it goes for you. All right. In the very first system, we have 2 equations. In the first equation, we know that y is equal to 5x minus 4, And our second equation says that x minus y is equal to 8. Do you see how this equation is already solved? We know y is equal to 5x minus 4. We have already isolated y. Y is already known and solved for. We also have x minus y is equal to 8. Neither variable is solved for here, but in that first equation, we have y all alone on one side. So I'm going to take this 5x plus 4, which I already know is the same thing as y, and I'm going to put it in for the y in the second equation. That's going to give me x minus. Now, instead of that y, I'm going to put 5x minus 4. Notice I'm putting it in parentheses. Putting it in parentheses. Because number one, I'm going to need to distribute the negative in this. But you never know what sort of situation you're substituting it into. So we want to protect it until we're sure. Equals 8. Now, here's the beauty. The beauty is the y is gone. It's been replaced by 5x minus 4. So now I only have x's in my equation. I've taken the 5x minus 4, which is the same as y, and I've taken that y out and replaced it with the 5x minus 4. I put it in parentheses to protect it. And now I'm going to work the algebra. So I've got x distributing the negative minus 5x minus a minus is plus 4 equal to 8. I've got x minus 5x. That's going to be a negative 4x plus 4 is equal to 8. Now, I'm going to subtract 4 from both sides, giving me a negative 4x is 4. Dividing both sides by negative 4. I now know that x is equal to a negative 1. Now, I have found the first clue. My first clue is that x is equal to a negative 1. Once I know that x is equal to a negative 1, I still want another color. I'm going to take this bit and put it in for the x up here. I know that y is equal to 5x minus 4. If the x is negative 1, then this has to be 5 times the negative 1 minus 4. That's negative 5 minus 4, which is negative 9. So now, I ran out of room, sorry. So now I know, that when my x is negative 1, my y value is negative 9. And this gives me the point, negative 1, negative 9. So without graphing these lines, I know that I should have a solution at negative 1, negative 9. Let's check. If I check this, is 5 times a negative 1 minus 4. That is indeed a negative 9. Check. Is negative 9. This isn't going to work as well. What did I do? X minus y. What did I goof up on? 5x minus 1. Oh, yeah, it does. Okay. All those negatives mix me up. So I've got a negative 1 is my x minus a negative 9. Is that 8? So that's negative 1 plus 9, which is indeed 8. Okay. Yeah, so it was the negatives. The negatives had me going. Right? So I have checked it in both solutions, and I know that this is a solution to my system. Beautiful. Beautiful. If you look at the second problem, we see that b is equal to 4. Now, don't get upset because it's a different letter. It's just a b. The other equation has a's and b's in it. Sometimes we get tired of x's and y's, and we use a's and b's, or m and n, or w and x, y and z. We can use any letter of the alphabet we want, all right? So we do know that b is equal to 4, and we know that 3a minus 2b is equal to 1. So I'm just going to take this 4, and I'm going to put it in for that b. This is not anything that is particularly difficult. We've done it a million times before, but when I present it with this lovely system bracket, cha-ching, cha-ching, oftentimes people get confused. Now, I'm telling you, b is 4. So this is going to be 3a minus 2, substituting in a 4, equals 1. Simplifying, 3a minus 8 is equal to 1. I'm going to add 8 to both sides. And I get 3a is 9, so a has to be 9 divided by 3 is 3. So our solution to this system, we know b is equal to 4. We know a is equal to 3. This gives us the solution, 3, 4. Now, I think the only question, well, maybe you got a lot of questions, but why did I do 3, 4 instead of 4, 3? Because A's come before B's. When you're not sure, put it in alphabetical order, or put it in the order of the letters alphabetically. Yeah. Okay. All right, problem number 3. Here we have x plus 3y is equal to a negative 15, and x is equal to a 2y. We already have an x is equal to 2y. We already know what x is solved for. We also have x plus 3y is equal to a negative 15. Since I already have this x solved for, I am going to take this 2y, and I'm going to put it in place of that x. Using parentheses to make sure, I have 2y plus 3y is a negative 15. That's 5y is a negative 15. Dividing both sides by 5, I have y is a negative 3. I know x is the same as 2 y's. If my y is a negative 3, then x should be 2 times that negative 3, and x should be negative 6. Notice I found the y first. Once I knew it, I put it in to solve for the x. This gives me the solution of x, y, or negative 6, negative 3. What does this tell me? If I were to graph these two lines, they would intersect at one point. And that one point of intersection would be negative 6, negative 3. The solution to a system, no matter what way you solve it, is the point of intersection if you were to have graphed it. Okay? All right. So now we kick it up just a notch, just a little bit. Sometimes when you have to use substitution, or when you feel substitution is necessary, you don't have a letter already solved for. In problem number 4, we see that example. Here we have 2x minus 3y is equal to a negative 4, and we have 2x minus y is equal to 8. We can solve for x's. We can solve for y's. But if you were to look at this, do you see how this first equation has 2 x's and 3 y's? That means I'm going to have to divide by 2 if I solve for x's, and I'm going to have to divide by 3 if I solve for y's. I could also choose to use the second equation. Here I have 2x minus 1y is equal to 8. If I choose to solve for x's, I'm going to end up dividing by 2's. If I choose to solve for this y, I'm going to end up dividing by 1. So I choose to solve for y's and I choose to use this equation. Why? Because the coefficient is lowest and it's easiest. So if I have 2x minus y is equal to 8, to solve this for y, I'm going to subtract 2x from both sides. So y would be a negative 2x plus 8. And then I'm going to divide everything by the negative 1. So y would equal, I'm going to write this part out. Negative 1, negative 1, negative 1. So y would equal 2x minus 8. Now that I have this solved for, I am going to take this piece, everything that y is, and I'm going to put it into the other equation. So 2x minus 3y equals negative 4. I'm going to put all of this in for that y. Okay? Here's the thing. You have to put it into the other equation. If you put it back into the equation you just did, you're causing, well, I don't know, you're just spinning in circles. I mean, if I use this equation to solve for y, and then once I have y, I put it back into this equation, I'm just spinning. I need to put it into the other equation. So that's going to give me 2x minus 3. It's only going in for the y. 2x minus 8 equals a negative 4. Okay? So that's going to give me 2x minus 6x plus 24 is equal to a negative 4. Notice I only have x's, and I can solve this by simplifying this side. Negative 4x plus 24 equals a negative 4 minus 24 from both sides. So I have negative 4x is equal to a negative 28. Divide by a negative 4. And I now know that x is equal to 7. I need to find both x and y. So now that I know what x is 7, I'm going to use what I had for y. Y is 2x minus 8. And I'm going to put that value in for the x. So that's going to be 2 times 7 minus 8, which is 14 minus 8, running out of room, which is 6. So now I also know what y is. Once I have both the x and the y, I know that there is a single solution at 7, 6. I now want to check it. To check it, I go back to the original equation. And to do that, I'm going to come down here at the bottom. I'm going to have 2 times 7 minus 3 times 6. That's going to be 14 minus 18. That's negative 4. Oops, sorry. And that checked with this guy. And then my second one is 2 times 7 minus 6. That's 14 minus 6. That's 8. And that checks with this one. So yes, I do know that that is the solution. 7, negative 6 is the solution to this system of equations. Yeah. Okay, 5. Next problem. Working on problem number 5. We see we have x plus 2y is 5 and 3x plus 4y is 11. I can solve for x's or I can solve for y's. Because this x is all alone by itself, I'm going to choose to solve for the x values in the first equation. So I have x plus 2y's is equal to 5. To solve this for x, I'm going to subtract 2y's from both sides. So x is a negative 2y plus 5. This is what I'm going to put in for x, not into the equation with the dot on it, not into the equation I used, but into 3x plus 4y is equal to 11. So all of this, the negative 2y plus 5, is going in here for that x. That's where it's going. I'm going to swap out just that x and put in a negative 2y plus 5. And then plus 4y equals 11. I got to include everything else there. Distribution of that 3 gives me a negative 6y plus 15 plus 4y is equal to 11. Solving, I can combine things here on this left-hand side. So I have a negative 2y plus 15 is 11. Now I want to switch that 15 over, so I'm going to subtract 15 from both sides. Negative 2y is equal to a negative 4. To further isolate the y, I'm going to divide both sides by negative 2. So we have y is equal to 2. Once I know what the y value is, I'm going to recall that x is a negative 2y plus 5. I got this from up here, right? That's why I put it in a box, because I knew I'd need it again. Only I'm going to take this y value of 2, and I'm going to put it in for that y. So now I'm going to have x is equal to a negative 2 times 2 plus 5, or negative 4 plus 5, which means x would be a 1. I think my solution, my single point of intersection for these two lines would be the point 1, 2. Now, I may want to check that with the original equation. If x is 1 plus 2 times y is 2, that's 1 plus 4, which is indeed 5. Oh, looky there, it checked. The second equation would be 3 times 1 plus 4 times 2. That's 3 plus 8, which is 11, and yes, it checks. Since it checks with both, my solution to this system of equation is 1, 2. Okay. Keep going. Great. Third example is 4g minus h is equal to a negative 5. Oh, and the second equation is 3g minus 5h is equal to 5. I have g's and h's. This is no different than x's and y's. I have decided that I'm going to solve for h because it is the only one without a non-1 coefficient. And I'm going to solve for h in that first equation. All right, 4g minus h is equal to a negative 5. In order to solve this for h, I'm going to subtract 4g from both sides. So negative h is a negative 4g minus 5. In order to eliminate the negative, I'm going to divide each term by negative 1. So we have h is 4g plus 5. Now, I'm going to take this mess for h. Since it's equal to h, that means in the second equation, 3g minus 5h equals 5, I can take out the h and put in everything that's in that box. Substitution would give me 3g minus 5. Just for the h, not for the 5. The 5 comes down. I'm only replacing the h. 4g plus 5 equals 5. So now I've got 3g minus 20g, 25, minus 25 equals 5. Right? Okay. I feel like this is going to be a little messy. Already, I feel like this is going to be a little messy. 3g's, 5h's, and a 5. 4g minus h, negative 5. Move that. Okay, yep, I'm just sort of checking my work here because it's about to get some messy. 3g minus 20g is a negative 17g minus 25 equals 5. Now I'm going to add 25 to both sides. And I have a negative 17g is equal to 30. Oh, this is ugly. Divide by a negative 17. G is 30 over 17, and that's going to be negative. Oh, that's ugly. That's not a pretty number. But this is where substitution works. Okay, so now I know what G is. Okay, now, since H is 4G's plus 5, I can take that minus 30 over 17 and put it in for the G. Oh, it's not going to be pretty. So H is 4 times a negative 30 over 17 plus 5. That's going to be a negative 120 over 17 plus 5. When you're not sure, you pull out your fraction button. So negative 120 over 17 plus 5. And I get H is a negative 2 and 1/17. Okay, so I believe EFGH, I believe the solution to this is a negative 30 over 17 and a negative 35 over 17. 17 times 2 is 34, plus 1 is 35. So I believe that is my solution. Oh, Lord, now I got to check it. Okay, so that's going to be 4 times negative 30 over 17 minus a negative 35 over 17. And I am thankful for fraction buttons on calculators. So I've got 4 times, parentheses, negative 30 over 17 minus, parentheses, negative 35 over 17. I got a negative 5. So the first one checked. But to be a solution, it's got to check both equations. So the second equation would be 3 times a negative 30 over 17 minus 5 times a negative 35 over 17. So 3 negative 30 over 17 minus 5 negative 35 over 17. And I got a positive 5, so both checks. Okay. So this is a solution to the system in number 6. That one was a crap ton of work. There is probably slim chance that I would give you that, at least not on a test. That would send you running for sure. But hey, just to prove to you, we can get through it. All right? So, can you use substitution to determine the solution to a system when one or more of these problems has fractions in it? Yes. Yes, you can. Let's us go. We just had one example. Let's see what we've got here. All right. The first example has y is equal to 1/3 x minus 1, and the second equation is 2x minus 3y equals 4. Notice we have already solved for y. Y is already solved for and ready to go, which is perfect because that means that I don't have to. So I know that the y is equal to 1/3 x minus 1. So I can take all of this and put it into the other equation. Where there is a y. Again, we're not replacing the 3. We are only replacing the y. So 2x minus 3. And then in parentheses, we have 1/3 x minus 1 equals 4. All right, the 2x will stay the same. I can distribute the 3. So a negative 3 times 1/3 is going to be a negative 1x. Negative 3 times negative 1 is a plus 3. This is going to give us x plus 3 is equal to 4. Subtracting 3 from both sides, x would have to be 1. Once I know what x is, I can put it back into y is equal to 1/3 x minus 1 for that x value. So I'll have y is 1/3 of 1 minus 1, or 1/3 minus 1. Again, with the fractions, use the tools available to you. Your calculator is definitely available. You can use the fraction button if you're not sure. 1/3 minus 1. Oh, turn it on, Amy. 1/3, there we go, minus 1, which is going to be a negative 2/3. This gives us the second value. This tells me I believe the solution is going to be at 1 comma negative 2/3. I then want to check. So if I'm checking in the first equation, is a negative 2/3 equal to 1/3 of 1 minus 1? Well, we already checked that. We know it works. What about the second equation? Is 2 times 1 minus 3 times 2/3, does that equal 4? Well, I know 2 times 1 is 2, minus, and I can use my calculator, Claire, to do 3 times 2/3. Oh, it's a negative, so 2 plus 2. Yep, that's 4, and it checks. Okay. That one wasn't so bad. What about problem number 8? Problem number 8, I've got 6k plus m is equal to a negative 1, and 2k plus 6m is a 3. I have k's and m's. I can solve for either, and I can use either equation. If I solve for the k, I'm going to have to divide by 6. And both the 3 and the 1 are not divisible by 6, not evenly. So I'm not going to do that. I'm not going to solve for that k. If I solve for k in the second equation, the 6 is divisible by 2, and the 3 is not. So I'm going to get a fraction, but the 6 will divide out. If I solve for the m in the first equation, the 6 will divide out by 3, but the 1 will not. If I solve for 6, nothing. So I'm either going to solve for the k here or the m there. I think I'm going to solve for the m's in the first equation. It's kind of a crapshoot. But I'm going to go for the m in the first equation. So I've got 6k plus 3m is equal to a negative 1. So 3m would be a negative 6k minus 1. And m, I'm going to divide everything by 3. Okay, so m would be a negative 2k minus 1/3. Okay, so that's what my m is, this mess. My m is this mess. So that means in my second equation, 2k plus 6m equals 3. I can take everything that's in this yellow box and put it in for the m. Not the 6. The 6 stays there. So I've got 2k plus 6, and then I'm going to use parentheses, negative 2k minus 1/3. Rest of this equation is equals 3. Simplifying, 2k plus 6 times a negative 2k is minus 12k. 6 times a negative 1/3 is minus 2, equals 3. So I've got 2k plus a negative 12k. That's going to be a negative 10k. Minus 2 is equal to 3. Adding 2 to both sides, negative 10k is 5. And dividing both sides by a negative 10, we get k is equal to a negative 5/10 or k is equal to a negative 1/2. Now that I know what k is, I can put it into the other equation. We know m is a negative 2k minus 1/3, which would be a negative 2. Since k is 1/2, I'm going to put that 1/2 in for the k. Sorry, negative 1/2. So negative 2 times a negative 1/2 is going to be a positive 1 minus 1/3. And we did this one a little bit earlier, but 1 minus 1/3 is 2/3. So I think I have a solution. Elemental p, k comes before. So I got negative 1/2 comma 2/3. And I think this is my solution. If I want to, I can check it. So we've got 6 times a negative 1/2 plus 3 times 2/3. That's going to be a negative 3 plus 2. That's a negative 1. Check with the first equation. In the second equation, I'd have 2 times a negative 1/2 plus 6 times a 2/3. That's going to be a negative 1 plus 4, which is indeed a 3. Check. So I do know that this one is a solution. Oh, I never put a box around this guy. So I can box that one. Whew. All right. Problem number 9 already has fractions in it. I'm going to be honest here, and I'm going to say that if I was given this particular problem, I would probably go ahead and solve this for x, just because it's easiest, right? The x is already positive and it's alone. So I'm going to start with x minus y equals 3. Solving it for x, I would add y, so x is equal to y plus 3. Now, I do have this solved, but my second equation, which is x over 4 minus y over 6 equals 1, it's already a mess with the fractions. And I might want to eliminate the fractions first. Okay, so to eliminate the fractions, we're going to do what we've done with just about any time we've had fractions. And we're going to multiply by the LCD. So the lowest common denominator for 4 and 6 is going to be 12. So I'm going to multiply both sides here by 12. And that's going to give me 12x over 4 minus 12y over 6 equal to 12. 12 divided by 4 is 3x. 12 divided by 6 is 2y. So before I complicated things, I wanted to get rid of the fractions first. Now, you could have done it in a slightly different order, and it still could be fine, right? Basically, when it comes to problems that start to get complicated like this, as long as you're playing by the rules, the order in which you make the changes doesn't matter. We can still get the same outcome. It's like redecorating a room, right? If you're redecorating a room, do you take all the furniture out first? Or do you just move stuff around? There are some things that have to get done, and maybe some things that should have a specific order, but really there's a little bit of a creative process that happens here. It's the thing that I like about math, but not everybody else does. Okay, so back on track. Now that I've eliminated the denominators, I figured out that x is the same as y plus 3. So I'm going to take this y plus 3, and I'm going to put it into this equation where that x is. I could have done it here, but it really doesn't matter where I do it. So I do have to put it in. And if I'd done it here, then I would have had parentheses and fractions, and so that is a choice I made. So then I got 3. And then in parentheses for that x, I got a y plus 3. Minus 2y equals 12. So 3y plus 9 when I distribute minus 2y equals 12. Combining my y's, y plus 9 is equal to 12. Subtracting 9 from both sides, y would be 3. I know now that y is 3. And from all the way up here at the top in the yellow box, I know that x is equal to y plus 3. Since y is 3, that tells me x is 3 plus 3, which is 6. Now, this tells me that I should have a solution at 6, 3. And I can check that by doing 6 over 4 minus 3 over 6. If I want to do it quickly, I grab my fraction button, right? 6 fraction 4 minus 3 fraction 6. And I do get a 1. That checks. And then I would also have 6 minus 3. Is that 3? Yep. So I know that this is a solution. Okay. Whew. Next page, last goal. Can we, using substitution, identify the 3 different types we talked about before? That is the inconsistent with the parallel lines, the consistent or singular, which we've done like 9 examples of. Well, no, I think we did 6 examples of it. And can we identify the dependent systems where one line is basically a copy of the other? Can we recognize those using substitution? So let's see. Okay. So here I have 4x minus 3y is 5, and 3y minus 4x is negative 5. It does not matter which one I solve for. I'm going to go here, and I'm going to solve for x's in that first equation. So that's going to give me 4x minus 3y is equal to 5, or 4x is 3y plus 5, adding 3y to both sides. Now I'm going to divide everything by 4. So x would be 3/4 y plus 5/4. This is not pretty. It is not pretty, but I'm going to take this. I'm going to put it into 3y minus 4x equals a negative 5. I'm going to put all of this in for the x. Just the x, not the 4, just the x. So that's going to be 3y minus 4 3/4 y plus 5/4 equals 5. That's going to give me 3y minus 12 over 4y plus, oh, nope. Yeah, it's going to be a minus. It's going to be a minus. Negative 4 times 5 is a negative 20, so minus 20 over 4 equals 5. So I'm going to get 3y minus 3y. Oh, I lost my negative. There we go. Minus 5 equals a minus 5. 3y minus 3y is 0. Minus 5 equals a negative 5. And I have negative 5 is a negative 5. Let me double check. 4x and 3y, I get 5. Divide everything by 4. X is equal to 3/4 y plus 5/4. I'm going to put all of this in. I kept the 3y. I kept the minus. The 4 came down. This x gets replaced by everything in here. 3/4 y plus 5/4 equals a negative 5. That's the mistake I missed the first time. So that's a negative 4 times 3 minus 12. 4 times 5 is 20. Positive, negative, negative. 12 over 4 is 3. 20 over 4 is 5. 3 y's, take away 3 y's, leaves nothing. I have a negative 5 is a negative 5. I could divide both sides by 5, negative 5. That would give me 1 is equal to 1. What does this mean? What does this mean? Since everything is equal, you don't have any x's left, you don't have any y's left, and it is true that negative 5 is equal to negative 5, and that 1 is equal to 1. These are true statements. So I don't have an inconsistency here. This is consistent because it is a true statement that 1 is equal to 1. So what we have here is the same line, copied. So it's the same line. It's been copied over and over. This is infinitely many solutions. This is using substitution, the outcome that you get when you have the same line being copied over. A consistent solution with a dependency. In other words, whatever works for one line will work for the other. You can mark this by saying there are infinitely many solutions. You can also mark this, since it is infinitely many, by saying from negative infinity to infinity, because the lines are the same from beginning to end. Okay? Note that this occurs when you get a true statement, such as negative 5 is equal to negative 5, 1 is equal to 1, 0 is equal to 0. That's when you know you have a consistent solution. You have a consistent system with a dependent solution. Okay? There are infinitely many solutions because the solutions of one line depend upon the solutions of the other. Okay. All right. Second problem. We've already solved for W. W is equal to 2z plus 3. By the by, I put a line through my z's so they don't look like 2's. That's why you see that line through there. Okay? All right, so I know that W is equal to 2z plus 3. Then I have 4z is equal to 2 and 2 plus W. Again, I can put this in for that W, but this is a bit of a mess, just like with the fractions. So I'm going to clean it up first. 4 plus 2W's. And now I'm going to put this in for that. So I have 4z is equal to 4 plus 2. Everything in that box is going in for the W. 2z plus 3. So now I have 4z is 4 plus 2 times 2z is 4z. 2 times 3 is 6. Cleaning this up, I have 4z's is 10 plus 4z. Now I want to subtract 4z from both sides. 4z minus 4z is 0 equals 10. 0 is equal to 10. Okay, let me just check. 2z plus 3, z plus 3. When I distribute that, I get 2 times 2 is 4, 2 times 2w is w. So I'm going to put all this in for there. So that 4z stays the same, that 4 stays the same, that 2 comes down, and instead of the w, I put in 2z plus 3. That's 4z plus 6. 4 and 6 is 10. 4z, subtract 4z from both sides, I get 0 equals 10. So I've done everything correct, and I got a false statement. This is false. This is a false statement. It's not true. What does this tell us when we get a false statement like this? This means that we have an inconsistent system. Something went wrong. Our system is inconsistent. There is no solution. And if you recall, when there was no solution, that meant that our lines were parallel. So in a graphing picture of these two equations, we would expect that the lines would be parallel. The false statement gives us no solution. The true statement gives us infinitely many. This is important to note. All right, last one. I have 2x minus y is equal to 3, and a negative 2x plus 4y is equal to a negative 4. So I'm going to go ahead and I'm going to solve for y's in the first equation. 2x minus y is equal to 3. Subtracting 2x from both sides. Negative y is a negative 2x plus 3. Dividing through by negative 1, y is 2x minus 3. I have isolated the y and solved for it. So now in my second equation, negative 2x plus 4y is equal to a negative 4. I'm going to put this box in where there was the y. Everything else will stay the same. Negative 2x plus 4. And then in parentheses, I'm going to have 2x minus 3. Close those parentheses. Equals 4. All right. Negative 2x plus 8x minus 12 equals 4. 6x minus 12 equals 4. I am going to add 12 to both sides, and that's going to give me 6x is equal to 16. Dividing both sides by 6 now, I get x is equal to 16 over 6, which does reduce, by the by, to give me 8/3. I know that y is 2x minus 3. If x is 8/3, this can go in where the x is. So I have 2 times 8/3 minus 3. Oh, I should have done that in the orange, and I didn't. Sorry. You can tell we're getting to the end here, right? Okay, so calculator, because it's fraction, and I like to know how to do those. 2 8/3 minus 3. That's going to be 2 1/3, or if you would rather, 7/3. Because I got both an x and a y here, this is again a consistent solution or a consistent system with a singular solution in xy. That tells me that were I to graph these two lines, they would intersect at a single point, right? So again, to sum up, with substitution, if you get a true statement, with no variables left at all, but the statement you get is true, like 5 is equal to 5 or 1 is equal to 1, that should tell you that what you have is the same line or a line and a copy of it. So these are the same line. If you were to graph them, you would have a consistent system with a dependent solution, meaning the answers to the solutions to one of the lines are dependent upon the solutions to the other, okay? If you're moving along with substitution and all of your x's and y's, z's and w's disappear, and you end up with a false statement like 0 is equal to 3. This is an inconsistent system, and there is not a solution. If we were to graph those, they would look like parallel lines. Our slopes would be the same, right? And lastly, for number 12, when we did substitution on that one, we got a value for x and we got a value for y. This is a consistent system with a singular solution. That solution would be the point of intersection were we to graph those two lines, right? Okay, so that is several examples of substitution. We've worked with substitution in simpler problems and problems with fractions. We've talked about what the 3 different solutions look like and what they would look like in terms of actually working them through and what they would look like on a graph. If you have any questions about any of these processes or any of the work that I did, please don't hesitate to reach out to me. The Math Center is also available should you need help on your homework and cannot get to me. All right. Thank you all. Have a good night.